Welcome to Learn a Lotl. My name's Nate, and in this video we're going to be looking at one of my favorite pieces of maths, which is this equation. Let's pop it into a calculator to see what it does.
Alright, so I've popped that equation into trusty Desmos, and I have this expression here, which is the one we're going to investigate in this video, and I have a slider so I can change the value of n. So n is a natural number, so I've just picked n can be between 1 and 20 and a step of 1, so it's only going to be integer values from 1 to 20, just so we can investigate the first few values that this equation gives us. So if I plug in n equals 1, I can see here that I get fn equals 1. If I use n equals 2, I get 1. If I use n equals 3, I get 2. N equals 4 gives me 3. N equals 5 gives me 5. N equals 6 gives me 8. Then I get 13, 21, 34, 55. Let's stop there. So it's already pretty crazy that this equation is only giving me natural numbers out, even though I have a square root 5, which is irrational. But you may have noticed that there's a particularly recognizable pattern to these outputs. So if we start at the beginning, I get 1, 1, 2, 3, 5, 8, 13, 21, and so on. This is actually the Fibonacci sequence. So in this video, we're going to investigate how and why this crazy looking equation gives us precisely the nth number of the Fibonacci sequence. Let's get into it. So the goal of this video is to derive this equation. The way we're going to go about that is we're going to write the Fibonacci, I'm going to say structure, that is the inherent structure, the meaning of the Fibonacci sequence, as a matrix equation. Matrix equation. And then we're going to use linear algebra techniques to derive from that matrix equation the equation we have above, the one we're aiming to derive. So this video is definitely aimed at those who've encountered linear algebra before. And if you have, I definitely encourage you to pause at any point you like in the video and have a go at the next step in the derivation or the rest of the derivation. And then you can continue watching to check how it weighs up against the method I'll show here. So without further ado, let's jump into the derivation. So we start with this structure of the Fibonacci sequence, or perhaps the definition of the Fibonacci sequence as a matrix equation. So the definition of the Fibonacci sequence is really that the nth term is equal to the sum of the previous two. So fn, the nth term, is equal to fn minus 1 plus fn minus 2. And n is a natural number. And we also have to kind of set the first two elements in this sequence to be equal to something, and we choose 1. So the first and second term in the Fibonacci sequence are defined to be 1, and then once you reach the third term, from there, this kind of recursive formula kicks in to define the rest of the terms. So we want to rewrite this as a matrix equation. So we want some matrix times some vector is equal to some other vector, and we want that equation to capture this recursive formula. So to do that, what we're going to do is we'll start with a column vector which contains the nth term in the Fibonacci sequence and the n minus 1th term. And we want this to be equal to some 2 by 2 matrix times matrix multiplied with column vector fn minus 1, fn minus 2. And if we compare this form to this recursive formula above, we can use matrix multiplication to fill in the gaps on this equation. So Fn is equal to Fn minus 1 plus Fn minus 2. So the top row of my matrix is 1, 1. And then similarly, the bottom row is going to be 1, 0. So this matrix, in a sense, captures this recursive structure of the Fibonacci sequence. Let's see how this plays out for the first few elements, starting from n equals 3. So for n equals 3, we have this column f3, f2, this column vector, is equal to 1, 1, 1, 0 times the column vector f2, f1. And f2 and f1 are set. They're kind of defined to be 1 in the Fibonacci sequence. So we can turn this into 1, 1, 1, 0 matrix multiplied with 1, 1. And that gives us 2, 1, which is what we hope to get, because we know the third term in the Fibonacci sequence is 2 and the second term is 1. So far so good. Let's try n equals 4. For n equals 4, we get f4, f3 is equal to this matrix multiplied by f3, f2. And what I notice is I could plug in f3, f2 because I figured out f3. But instead what I'm going to do is actually plug in this matrix multiplication for f3, f2, because I know that's equal to f3, f2. So this becomes 1, 1, 1, 0, matrix multiplied with another matrix 1, 1, 1, 0. So this matrix is squared, and then f2, f1, which is 1, 1. And at this point, we actually have a pattern. We can generalize this, that for any n greater than or equal to 3, we have fn minus 1 is equal to this matrix 1, 1, 1, 0 to the power of n minus 2, 1, 1. So feel free to have a go at the n equals 5 case. You'll see you get a similar thing as we got for n equals 4, except you'll have that matrix cubed. And at that point, we can recognize that there's a bit of a pattern going on. And this is a good place to be at this point, because we no longer have a recursive formula. We no longer have the nth term in the Fibonacci sequence defined by some equation involving previous terms. So we've changed the problem. It's no longer a problem of a recursive equation. Now it's a problem of a matrix to an arbitrary power, because we don't know the value of n. This is a general formula. So we have this 1, 1, 1, 0 matrix to the power of n minus 2. But fortunately, in linear algebra, we have a technique to determine matrices to an arbitrary power. What we're going to do is we're going to diagonalize this matrix 1, 1, 1, 0. And I'll point out here that not all real matrices are diagonalizable, but this one which we're looking at is. So we are going to be able to diagonalize this matrix. So to diagonalize 1, 1, 1, 0, we want to find its eigenvalues and eigenvectors. I will leave it to you to determine that the eigenvalues we get are 1 plus the square root of 5 over 2 and 1 minus the square root of 5 over 2. In fact, because those two eigenvalues look very suspicious given the formula we're aiming for at the end, we have those square root 5s popping up now. So I might just below find one of the, or find these eigenvalues as an example. So in order to find the eigenvalues, we consider this characteristic equation. So lambda I minus A, where this matrix we're looking at is A, equals 0. So that gives us the determinant of lambda minus 1, 1, minus 1, minus 1 lambda, which is lambda, lambda minus 1, minus 1, and that's equal to 0. So we have lambda squared minus lambda minus 1 equals 0. And I'm going to solve this quadratic by completing the square. So I get lambda minus half squared. And then I've also got a plus 1/4 in that. So I need to subtract 5 over 4 equals 0. So I get that lambda minus a half is equal to plus minus the square root of 5 on 2. So I'm skipping a few steps there, but then from that I get lambda is equal to 1 plus or minus the square root of 5 over 2. So there we go. We get those suspicious looking eigenvalues which do appear in the equation we're looking for. So this is another good sign that we're on the right track. So if you go through with the rest of the diagonalization, you should get that for this matrix 1, 1, 1, 0 that we're looking at, we can represent it as this matrix product A equals SD S inverse, where D is diagonal and S is invertible. And you should find that if we choose D to be given by 1 plus the square root of 5 on 2, 0, 0, 1 minus, so I'm choosing that to be the order of the eigenvalues for my diagonal matrix D. I should get S is equal to 1 plus square root of 5 on 2, 1, 1 minus the square root of 5 over 2, 1. So those are my corresponding eigenvectors. So for that eigenvalue, I get this eigenvector, and for that eigenvalue, I get this eigenvector. And then if I invert that matrix, which it's a 2 by 2, so I can apply a quick formula to invert. I should get 1 over the square root of 5 outside of 1 minus 1 minus 1 minus the square root of 5 over 2 and 1 plus square root of 5 over 2. And this is very helpful because diagonalizing allows me to take arbitrary powers of this matrix easily, because I can turn it into arbitrary powers of a diagonal matrix, which is easier to do. So now I just want to put everything I've done together. So what have I got? So far, I have that Fn minus 1 is equal to this matrix 1, 1, 1, 0 to the n minus 2 times 1, 1. And I have that 1, 1, 1, 0 to the n minus 2 is equal to that matrix S I found, so 1 plus square root of 5 over 2, 1, 1 minus the square root of 5 over 2, 1, times that matrix D I found, 1 plus square root of 5 over 2, 0, 0, 1 minus the square root of 5 over 2. And then that matrix S inverse I found, 1 over root 5 outside of 1 minus 1 minus 1 minus the square root of 5 over 2, 1 plus the square root of 5 over 2. So, and of course, my diagonal matrix D is to the power of n minus 2, which I forgot to write. Whoops. So this is what I have. Now I can rewrite this. Let's pull that 1 over square root 5 out the front. Then I have, maybe let's just for the sake of simplicity, let lambda plus equal 1 plus the square root of 5 over 2 and lambda minus equal 1 minus the square root of 5 over 2. This is just going to make my next line look a bit cleaner, but Because these numbers are popping up quite a lot. So I have lambda plus 1, lambda minus 1. Then I have lambda plus to the n minus 2, 0, 0, lambda minus to the n minus 2. So that's my my diagonal matrix D to an arbitrary power. Very easy to calculate. And then finally I've got S inverse, which is 1 minus lambda minus 1 lambda plus. And then for my next line, I'm going to matrix multiply these two together. And I get 1 over the square root of 5 outside of, let's do this matrix multiplication, I get lambda plus to the n minus 1, and then I get lambda plus to the n minus 2 from matrix multiplication, and then for my next entry, I'm going to have lambda minus to the n minus 1, and lambda minus to the n minus 2. And then that's going to be multiplied with S inverse, which is 1 minus lambda minus and lambda plus. All right, so then I want to put that all together, and I'm going to get 1 over square root of 5. Let's see. Hang on. At this point, the matrix multiplication is going to be very complicated. So what I'm going to do is go about it a slightly different way, just to make it even simpler. So let's get rid of that and rewrite what we have on the next page, and we'll simplify this calculation. So we have fn minus 1 is equal to 1, 1, 1, 0 to the n minus 2 times the column vector 1, 1. And from that calculation I did before, I can rewrite this as 1 over the square root of 5 outside of lambda plus to the n minus 1, lambda plus to the n minus 2, lambda minus to the n minus 1, lambda minus to the n minus 2, times that S inverse matrix, so 1 minus lambda minus, lambda plus, and then also times that column vector 1, 1. So to simplify what, this matrix multiplication would get quite complicated. So instead of doing that one next, I'm going to do this matrix multiplication next, because that would be slightly simpler. So I get 1 over the square root of 5, lambda plus n minus 1, lambda plus n minus 2, lambda minus n minus 1, lambda minus n minus 2. And then let's do that matrix multiplication. I get 1 minus lambda minus and minus 1 plus lambda plus as a column vector. And here we note that 1 minus lambda minus is equal to 1 minus the square root of 5 over 2, which is equal to 2 minus 1 plus the square root of 5 over 2, which is equal to 1 plus the square root of 5 over 2, which is equal to lambda plus. And similarly, minus 1 plus lambda plus is equal to minus 1 plus the square root of 5 over 2, which is equal to minus 2 plus 1 plus the square root of 5 over 2, which is equal to minus 1 plus the square root of 5 over 2, which is equal to minus 1 minus the square root of 5 over 2, which is equal to lambda minus, or minus lambda minus. All right, so we're almost through to the end. At this point, we have this column vector fn minus 1 is equal to 1 over square root 5 of lambda plus to the n minus 1, lambda plus to the n minus 2, lambda minus to the n minus 1, lambda minus to the n minus 2, times this column vector that we're going to simplify, which from before gives us lambda plus and minus lambda minus. So now we just do that final matrix multiplication, which is going to give us a column vector. And that column vector is going to be, our first element will be lambda plus to the n minus lambda minus to the n. And our bottom element will be lambda plus to the n minus 1 minus lambda minus to the n minus 1. And if we rewrite this, subbing in our lambda plus and lambda minus values, which we only kind of used for a bit just to make it easier to write out, we get that fn minus 1 is equal to 1 over the square root of 5 times this other column vector, which is 1 plus square root 5 over 2, that's our lambda plus, to the n, minus 1 minus the square root of 5 over 2 to the n, and then 1 plus square root of 5 over 2 to the n minus 1, minus 1 minus the square root of 5 over 2 to the n minus 1. And that is actually it, because if we look at our top element and our top element with that scalar out the front, that is the equation we're looking for. We have fn equals 1 over the square root of 5 outside of 1 plus square root of 5 over 2 to the n minus 1 minus the square root of 5 over 2 to the n. And then if we look at that bottom element and this equation with the scalar out the front, it's the exact same thing, but instead of n, you have n minus 1. So that's actually the end of the derivation. So if you're wondering, like me, how does this equation give us the Fibonacci sequence? This sequence of calculations we've done, this derivation we've just completed, is why. Because if you write the Fibonacci sequence as a matrix equation and use the techniques of linear algebra to diagonalize the matrix and turn a recursive formula and a recursive structure into more of a function where you just plug in a value of n and get a number out, you get that equation. Even though there's this square root of 5 hovering all over the place, which is irrational, this equation has to give you the Fibonacci sequence, because that's where we got it from. We got this equation from the Fibonacci sequence. So I hope you enjoyed that journey as much as I did. I love this piece of maths. It's super cool, super exciting. We get to see how these completely different ideas interact, which is what maths is all about, these cool discoveries and explorations and ideas. So I hope you enjoyed it as much as I did. If you enjoyed it, leave us a like, subscribe, and feel free to drop a comment down below if you have any thoughts or ideas for the channel, and I will see you in the next video. Thanks.